Hello students, in this video we'll discuss the wave equation, causality, domains of dependence, and domains of influence. Let's be given the one-dimensional wave equation. UTT equals c squared uxx with initial data ux0 is phi of x and x0 is psi of x. This is your initial position or configuration. And this is your initial velocity. Okay. And of course, what's our domain over here? Our x is a real number, and our t is greater than or equal to 0. Okay. So we're solving this on the upper half space, right? And so what's the idea? So we have D'Alembert solution. So recall that under the change of coordinates, under of coordinates, mu equals x plus ct and eta equals x minus ct. Under this change of coordinates, what happens? The structure of the wave equation turns into just u mu eta is equal to 0, right? This implies that u mu eta is equal to 0, and this gives us the D'Alembert formula. This implies that u is a constant function. U can be written u of mu and eta is just a function of mu plus a function g of eta, like so. That's the general solution to that PDE over there. And therefore, by plugging in the initial conditions, we've proven, did this in a different video, we get D'Alembert's formula, right? D'Alembert's formula. And what's the formula? The formula says that u of xt is 1/2 phi of x plus ct plus phi of x minus ct. Those are the characteristics, right? Plus 1/2c, the integral from x minus ct to x plus ct, psi of s ds, okay? So now what we want to do is look at these terms individually and see what's going to happen over here. So what's happening with this term over here? So this term over here, what does this term over here in the solution do, right? This takes the initial profile, geometrically, takes the initial profile and moves it to the right and left with half the amplitude. Okay. This one's going to the right, that one's going to the left, right? And so the wave, if it starts like this, is going to split down like that. So that's how that goes. And then what does this other term over here do? This term is the velocity term, and this term over here is going to move. This moves ds. This moves the waves, initial profiles, at a speed less than or equal to c. Okay, that's the key feature. The speed of this curve over here is less than or equal to c. So this is an example of what's known as finite speed propagation. So that we say that the wave equation has finite speed of propagation. Okay, that's a very important idea, finite speed of propagation. What's the whole point of this is that what's happening over here. That means that if I give you an initial point over here, it's either going to move to the right like that or to the left like that, but it can't go beyond a certain level, beyond an aperture of the inverse tangent of c, right? Because that's telling you that you cannot get outside a particular region, so only parts of the space are determined in other parts, right? Now what do I mean by that? Let's be more precise with that. So what I mean is the following two things. We have the domain of influence. So here's the x-axis. Here's the t-outs with the t-axis over here, right? There's the t-axis. If I give you a point, xc, 0, so I give you that point over there, what can this point do? It can go over here along this characteristic, and that's the characteristic x minus ct equals xc. Or I can go backwards along this characteristic over here. This is what? This is x plus ct is equal to xc, right? So in other words, this is the domain of influence for this point over here. So this domain over here, this inside this triangle over here, this triangular region, this ray, is the domain of influence of xc. Okay? What about the domain of dependence? Well, I can also do the same thing starting at a point in the xt plane, right? So here's the x-axis, here's the t-axis. And what can I do? Then I can pick a point over here, xt, and I can go down over here, or I can go down over here. What are these points over here? So this first point over here is what? This first point over here is just x minus ct. This point over here is just going to be x plus ct, comma 0, right? And then what's this region over here? That region is called the domain of dependence. This is the domain of dependence. In other words, any point inside this domain of dependence over here, any given point, if I look at its propagation, that point xt will reside in the domain of influence. So no matter what point I choose over here in this domain of dependence, it will always be the case that whenever I draw this domain of influence, it will always encapsulate xt, therefore it's the domain of dependence. But notice, of course, too, that what do we see? We see that for this point xc0, there's points that are outside the domain of influence, and that's exactly what is meant by the finite speed of propagation. So in other words, I'm only propagating out at this speed c, right? So in other words, the speed c is dictating everything over here. And we see this example with we saw this example in geometric optics when we talked about like the light cone and the Monge cone. This is the same sort of idea here, the idea being that you can only move out at a certain speed. We're going to see with diffusion processes that diffusion processes have an infinite speed of propagation, and that gives a clear delineation between a hyperbolic problem and a parabolic problem or an elliptic problem. So we'll see that in further videos. Thank you very much.